tonight is one of the first nights after a very, very long time that we're getting to do some observational astronomy using the SOAR telescope, which is in Chile. But we are not in Chile. I am in my house, and Zach and Derek, my fellow research group mates, are in Chapman Hall at UNC in the remote observing room. And we all work with Dr. Sheila Kannappan on doing cool stuff, like observing galaxies and figuring out how they're born and what they do after. And I will hand it off to Sheila.
All right, thanks, Mugdha. I will share my screen. So as Mugdha mentioned, we are observing with the SOAR telescope, and this is that telescope. We imagine that it might be just that beautiful, though we're not there. And inside that telescope dome, here is kind of the guts of the backside of the telescope with one of my former graduate students working on the Goodman spectrograph. We sent Katie, my former student, down there because we built a custom back end for the spectrograph. And this is a view of the design schematic and then a picture of the actual object from the opposite side view of the design schematic. And what it does is it allows us to take spectroscopy along 3 parallel lines on top of the galaxy. And this picture on the right shows those 3 parallel lines arranged on top of a spiral galaxy. And the color there shows Doppler shifts. So the red shifts are moving away from you and the blue shifts are moving towards you. And so this is a way of measuring that the galaxy is rotating. And as you may have heard at some point, galaxies rotate too fast. They rotate too fast for the amount of mass that we can see that they have. And this was the first way we knew that there's a mysterious stuff out in the universe called dark matter. And in fact, there's more dark matter than there is normal matter. And what Resolve is allowing us to do is to map out that dark matter. Now, this is a very different picture. In this picture, each dot is a whole galaxy, and the black dots are the dots in our survey. Our survey is called Resolved Spectroscopy of a Local Volume. So for each one of these dots, we're getting one of those spectroscopy data sets like you just saw that might tell us all about its rotation and other internal dynamics and chemistry. And we can map that out for each individual galaxy in this large scale pattern where you see there are voids and walls and filaments. It's kind of like a giant spider web. So it's called the cosmic web.
This, what you're looking at, is the Goodman spectrograph control panel. So when we're observing galaxies throughout the night, this is a team effort with the telescope operators in Chile who are actually at the telescope. And that effort involves them actually controlling the telescope while we control the spectrograph remotely, right here from our observing center in Chapman Hall. And so what you're seeing in the bottom panel with all the blue, yellow, red boxes, that's controlling the motion of the spectrograph, the camera angles, the grading angles, what diffraction grading we're going to have installed, what focus for the camera, for the collimator. So this is all the mechanical aspects that we want to control. And in the upper section, this is where we specify more electronic parts, like what file do we want to, what do we want to name the file for the target that we're observing right now, and what lamps do we want to have on for calibrations, what kind of calibrations are we doing. So this interface allows us to work directly with the telescope operators in Chile so that we can obtain our science goals throughout the night.
So some of the other science that happens in this research group is that I look at something called nuggets. They're pretty important because they are the connection between the tiny dwarf galaxies and the most massive galaxies in today's universe. On the left, I have an image of one, and you can see that it's a pretty compact galaxy, and that's what nuggets are for the most part. And this is actually one that we're observing spectra for, so we can get a better idea at what its kinematics are like.
So what you can see here is one of our targets in different stages of our observing process. So the first thing that we do is take an image of the galaxy, which is the far left. You can see this really pretty galaxy with complicated, interesting structure. My science is focused on trying to find black holes in the center of dwarf galaxies, which are little galaxies that are actively eating up the material around them. And that makes them quite bright, observable. And the fact that they're in these small galaxies also means that the black holes are small. So we can learn a lot about the evolution and the growth and the effect that the galaxy and the black hole have on each other, and also how they might evolve into bigger galaxies and bigger black holes like the Milky Way, the one that we live in.
So I've done a lot of work automating the reduction of data we get from the Southern African Large Telescope. And data reduction is basically just taking the image we get from the camera that sits behind the spectrograph and turning that into a spectrum, which has wavelength on the x-axis and intensity of light at that specific wavelength on the y-axis. And that's been in service of my project, which is exploring a new galaxy formation mechanism. So when we typically think of galaxies, we often think of the Milky Way, which is a spiral flat galaxy that's kind of pancake shaped. But galaxies come in all shapes and sizes, and on the other side of that spectrum is a purely elliptical spherical galaxy that's shaped like a ball. And our traditional wisdom tells us that galaxies are going to crash together and merge and combine a lot. And you would kind of expect that the ordered motion of a flat galaxy would randomize out into a ball galaxy in that case. But what we actually see is this can't be a generalization, because we observe a lot more disky galaxies in the sky than ball galaxies. So I've been looking at radial cutouts of statistics associated with the kinematics of galaxies to try and explore a process we call disk regrowth, which is where over a long period of time, a disk forms around the center of a ball galaxy, which will eventually turn it into a more disky galaxy, which is what we would expect.
So my project is working on developing a galaxy group finding method that finds groups like the local group. And the local group is the galaxy group the Milky Way is part of, with Andromeda, which is the other giant galaxy, and then a bunch of other smaller galaxies. And the local group is still in the early stages of formation. The galaxies in it are gravitationally bound, but the group hasn't really settled together yet. And most galaxy group finders tend to find groups that are in the later stages of formation and more settled and closer together. The galaxies are closer together. But a lot of group finders miss groups like the local group. So with this new group finder, we can identify groups like the local group and get an idea of how common galaxy groups like our own are in the universe.